so let's get started. Okay, so basically the current problem is that existing robots, basically can manipulate rigid objects. So for instance, they could pick up, like a rigid object, for instance, this laser pointer, and move it someplace else. However, ideally, in order for robots to be useful, for instance, around the house, they should be able to manipulate deformable objects. For instance, they should be able to tie a knot, or fold clothing to help with laundry, or perhaps perform surgical suturing. Okay, so how do we do this? Well, we use something called learning from demonstration. The general idea of that is that a human will perform the task. In this case, it's tying a knot in the rope. And then the robot will observe the demonstration and learn from that and be able to perform it by itself. So here's the video of a human performing a demonstration. So notice how he's picking up, manually moving the grippers, and he's manually commanding them to open and close, and in doing so, tying the knot. Okay. And so the robot has to be observing this. One of the sensors it has is a depth camera. So a Kinect camera is a depth camera. And these capture point clouds. A point cloud is essentially like a normal image, except for each pixel, instead of a color value, it senses a depth or a distance to the camera. Okay, so there's kind of two phases with learning from demonstration. One is the demonstration phase, and the other is the execution phase. So in the demonstration phase, so this is while the human is performing the demonstration, the robot records where the rope is, and this is captured both from a color image and from the point cloud, remember that's the depth image. And this is used, the color image is used to select out the points where the rope is. So that basically tells the robot where the rope is. And it also captures the position and orientation of the gripper. We call this the gripper trajectory. Okay, so next is the actual execution phase. How does this work? Well, it first has to perform a transformation. So basically a transformation is just a function, in our case, that maps points in 3D space to other points in 3D space. So how does our specific transformation work? Well, let's imagine that we have a rubber sheet here, and we kind of grab it by these 4 points. I'll call them the key points. And we also drew a grid on this rubber sheet. And now we stretch the rubber sheet by moving the key points. And now you can see via the grid that we drew on it that it's been deformed. So this is in the demonstration phase, this is the test phase. Now, remember we also captured the gripper trajectory. So if we draw a trajectory on the sheet, then we can see that the trajectory has also been warped after we've dragged the key points. Okay, so how does this actually work? Well, if you look at the demonstration, the red points are where the rope is. So that's captured from the point cloud. And the solid red line is the gripper trajectory. So basically, this is during the demonstration, and the gripper picked up the rope there and moved it across here and set it down there. Okay, so that's demonstration phase. And now this is the test phase. And so there's a new rope shape, and there's a new point cloud. So now the new point cloud are the blue dots. And now the transformation has been applied. Remember that's that's calculated from the point clouds. And you can see this new gripper trajectory that's been computed. It has the general shape of the demonstration trajectory, but it generally follows the test rope shape. So it looks like that should work. So basically that's how the gripper's positions are calculated. How does the gripper orientation get calculated? This is more complicated since the transformation applies only to the gripper points, not the orientations. So there are actually many different valid transformed orientations for the same point. So which is the correct orientation? Well, the basic idea is that we want to keep the gripper perpendicular to what it's gripping. So So essentially, if you look at this diagram, the rope is laying on the table, and then the gripper is coming down like this, and the camera is above it. So those are the two gripper points. And so the key point to look at is we make the assumption that the rope is going to be perpendicular to the grippers. So the red line is exactly perpendicular to the grippers, and the rope is approximately perpendicular to the grippers. So that's in the demonstration phase. Now in the test phase, we can see via the blue grid that there's been a transformation or warping. And now the rope is approximately still perpendicular to the red line. And essentially, the orientation we choose is keeping the grippers perpendicular to the red line. And that should, in effect, keep the grippers perpendicular to the rope, so we'll be able to successfully make it grab. Okay, so here is a video of executing. In the upper right-hand corner, you can see the transformation process. So it's currently capturing a point cloud and then doing the transformation. And here it's going to successfully figure out where the rope ends are and successfully move them to the right place for the transformation. Okay, so it's successfully able to tie them on. Okay, so to recap, in the demonstration phase, the robot records where the rope is and records where the gripper is. In the test phase, first it has to capture a new point cloud. It finds the transformation from the basically the old rope to the new rope. It applies this transformation to the trajectory of the gripper, and then it executes this new trajectory. Okay, so that's what you just saw in that video. So now that works great if you only have one demonstration, but what if you have multiple demonstrations? So you have multiple demonstrations, basically to cover a larger space of the different object states. And in order to do that, in order to basically use multiple demonstrations, you have to figure out which demonstrations are similar to other demonstrations. The simple way to do that is to actually look at the transformation. And so the robot calculates this number called the warping cost. If the transformation is simple and there's less distortion, then there's going to be a low warping cost. If the transformation is more distorted, then the warping cost is going to be high. Okay, so let's just try picking the demonstration that when transformed with the test point cloud results in the lowest warping cost. Okay, so that means that the rope, we pick basically the demonstrated rope that looks the most similar to the test rope. And it turns out that this is not actually much better than just using one demonstration. So why might this be? Well, let's look at ideally how the warping cost would look like. So here's a graph, an idealized graph of the warping cost versus the execution quality. So 4 would be a complete success, and 0 a failure, and then these numbers are in between. So ideally, there'd be some threshold for the warping cost, under which it would always succeed, above which it might fail, and then a nice grid in between. However, when we kind of run this on the actual robot, it's a slightly different story. So you can see if the warping cost is less than 5, then it always succeeds. There's cluster points there. But if the warping cost is greater than 5, it's more random how the robot actually performs. Okay, so what's a potential solution? This is kind of like future work. So basically, we modify the test procedure. Like before, we capture a test point cloud. Now this is different. We save the test point cloud because we'll use it in the future. Now instead of just choosing the demonstration with the lowest warping cost, we look at all of the saved demonstrations and all of the saved test point clouds from all of our previous tests, and we pick the lowest warping cost out of all of them. We find the transformation like before, apply the transformation, and then save the trajectory. And then, of course, execute on it. And so this should hopefully be able to learn much better what the desk demonstrations are. I'd like to thank Professor Pieter Abbeel, my graduate student John Schulman, and the undergraduates in the lab, Henry, Jonathan, and Kush, and of course, Surf and the Rose Hills Foundation.